Hi, my name is Bruce, and today I'm going to talk about the paper is called the Variable Temperature, Salinity, and Water Mass Structure in the Southwestern Taiwan Strait in summer. And first of all, the study is in the Taiwan Strait, and what is what is what is Taiwan Strait? Where is Taiwan Strait? And it is over here. It is a crucial channel to connect the South China Sea and the East China Sea here. And it has a complex bottom topography and current systems, and such as like crucial or something coast China currents, whatever. And this place is under the influence of the monsoon wind. So there's the oceans here also has a seasonal change, and this place have many temperature and salinity variation studies here, and the water mass structures in summer are complex, especially the upwelling event. And this study is going to find the upwelling event to see the water mass structure in summer. Yeah, and oh my god. Okay, so what is the purpose of this paper? Is the first is identify and classify the major water masses, and there we're going to depart five departments of water masses, and I will talk it later. And second is expand the spatial and temporal variability in temperature and salinities, and eventually will find the factors influence hydrographic variations. So let's talk about the data source and data processing. This is from China's paper, so the research virtual is from China, yeah. And there's a full summer course in 2004, 2005, 2006, and 2007. And they use the SBE 917 plus CDD profile at variation depths at 5 meters, 10 meters, and 20 meters, 30 meters. And finally, they use the Fuzzy clustering method to classify the water masses, and I will talk it later. Yeah. So let's talk about the station map. This is the picture A is a summer occurs in 2004, and B is 2005. And in the picture A, you can see the study area is in the specific area, which is like this place is much shallower than other places. This is called the Taiwan Banks here. So the study is in this area is near the Taiwan Bank. So yes, and the C and D is the summer occurs in 2009 and 2006 and 2007. Yeah. So the research first do the summertime mean temperatures in a horizontal way. So you can see the picture A. It is at a depth of 5 meters, and you can see they plot the temperature contours here and use the selection A, selection B, and selection C to make the contours here, and at a depth of 5 meters, 10 meters, 20 meters, and 30 meters here. And then they do the vertical weight for the section A, for example, like this. They use this to make the summertime mean sectional distribution of temperature and salinity, and use this to I don't know I don't know whatever it is to use the methods which is mentioned above is Fuzzy clustering methods to classify the water masses here. So they will plot the figure on the left hand side, and it is called summertime mean water mass distributions. And there will be 5 departments in the water mass distribution structures, and I will talk it later. And the figures, the tables here is the water mass structure department, and you can see each of them have a specific temperature range and salinity range, and we'll talk it later. And the first of all is coastal dilute water, and it is low salinity waters found in the surface layer of a western Taiwan bank, which is there. And it also represents like there's a river put into the oceans where the river put the oceans. Yeah. And the next is upper warm water, and it is mainly distribute in the upper layer of the South Taiwan Straits. And nothing can tell. Yes. And next is mixed water, and you can see the pictures here. It is dominant water mass in this picture, and it has a intermediate temperature and salinity values here. And the fourth is upwelled water. It is the main characters here, because you can see that there's on the coastline, there's a low temperature, high salinity water originating from the subsurface layers of north and southern China Sea. And this happened the upwelling event, and this area is also enhanced too. And the last part is subsurface water, and you can see that this water mass is typically below the 130 meters southeast of a Taiwan bank, and it has a low temperature and high salinities here. Yeah. So we will talk about the next part. Oh, so this figure is the summertime mean water mass structures. So the next part is analyze the data in individuals, and this is 2004. This two picture is the sectional temperature and salinity distribution for course in 2004. And this is temperature, this is salinity, and also use the method I mentioned above to plot the water mass structure figure like this. And so does 2005, 2006, and 2007. So in 2004, you can see that the coastal diluted water was absent. There's no, I don't know where this color is. It's maybe dark green. I don't know. Not on the coastline. And upwelling was a minimum. There's not strong upwelling is here. And in 2005, I remind you to remember this year, because there is obvious to see there's a strongest upwelling events with a widespread low temperature and high salinity water along the coast. It's like this. And 2009, there's also a upwelling too, but it's not that larger than 2005. And upwelling was concentrated south of Nan'ao, NA. So the next year is 2007, and you can see there also a large upwelling event here, convergent aboard coastal region in southern Fujian, like this. So we talk about the influence of these events. So the first of all is the wind. These four pictures is wind data during the course in 4 summer years, and the two red lines here means the research period. So what we mentioned in 2005 and 2007, there's a very obviously upwelling here, and you can see the wind direction here is strong southwesterly winds and persists for about 10 days, and so does the 2007, but it's not that strong than the 2005. So this in 2005 and 2007, there's a strong southwesterly wind, so it caused the coastal welling. But in 2004 and 2006, the wind is not that steady, and it's changed with the time. So we can get a get a conclusion that the southwest or south wind help cause coastal welding, while north and changing wind stop it. Okay. So next, it used the numerical model simulation, and you can see that the right-hand side is the left-hand side is the southwesterly wind, and the right-hand side is the northeasterly is the wind. So you can see the low temperatures here is extends much more higher than the northeasterly wind is. So you can tell that the southwesterly wind causes the much more powerful upwelling events here. Okay. Then the other two factors of upwelling maybe it's like ocean current and topographics here. And the currents will bring this place north of the South China Seas. There's a nutrient-rich water and cold waters here, and and the topography. What I mentioned is because the Taiwan Banks is here, so like this area is like a slide, and this current will push this nutrient-rich water and cold water to opposite way to the slide into the study areas here. So it will cause the upwelling events here. And so let's get a conclusion. There's two factors here to enhance upwelling events. The first is the persistent strong southwesterly winds, and second, the deep channel western of a Taiwan Bank. This is, you can imagine that there's a slide that the nutrient-rich water and cold water to push into the study regions and cause the coastal upwelling events. And when the coastal upwelling events happens, and the salinity, water mass structure, and temperature will change a lot. So that is the paper's conclusion. So that's all. Thank you.
I'm not sure if I didn't catch you. May I ask the purpose of this paper?
Oh, this is kind of be a purpose here because the Taiwan Straits is the water mass in summer are complex, and there's especially in the upwelling event. So the researcher have to research they put the CDD to the ocean to get the data, analyze the water mass in summer and how upwelling happens, and the water mass structure, how compressible it is, and yeah, that's it.
Okay, and may I ask the page 18? I'm not sure. Oh, I don't know what happened here. And you.
It is a data analysis. They just show the pictures and they didn't mention why it is like this.
So could you explain it?
Oh, can I explain this? To this picture, the first picture A in 2004. There you can see the wind, and we get a conclusion that the upwelling is caused by the wind, right? So the wind here is not that steady southwesterly winds or southerly winds. It is changed a lot. So the upwelling is not seen in the 2004. So this might be the picture is not much coastal dilute water or the upwelling water here.
Okay, thank you.
How about it change the shape will
I don't get it.
affect to the result?
You mean that change the point direction?
Yes.
Will the results change? I think it is. The answer maybe is no, because they do the 4 years, and the point here is I see is not the same. So I think the data is much 可相信的怎么讲？不会讲。哈，that was okay.
Okay, thank you.
I don't know how to read it. And the minus is the is the west. And
This is the wind direction.
and
You mean
the,
this?
the minus is the direction.
The minor is a direction.
The YSL.
Why? Oh yeah, yes.
It is the west. The west.
Oh, oh, I know. Oh yeah. It's a good question.
Where's the
But
north and south?
the positive is north way.
Oh.
The negative is south way.
Oh.
No, so the 2005 and 2007 there's a north wind here.
So the west is
The west is
is
the
that left or right?
left or right is mean the east and west.
Oh, east and west.
Yeah, but
East, west. Oh,
got it.
maybe.
Okay.
I actually had a similar question as her because how do you get the conclusion of that southwest or south wind help cause coastal upwelling? How do
Okay.
you get the
I
conclusion?
will talking again. So in these 4 years, we mentioned that in 2005 and 2007 there's a large and obviously upwelling events here. So we use the wind data to see what is going on this period. And in 2005 and 2007, there's a very obviously to see that there's strong southwesterly wind persists to blow like this way, and so does the 2007. But in the 2004 and 2006, the wind is changing. So the upwelling event is not so obviously and even didn't show up on the pictures here.
The good thing of this talk was you can see that he was very fluent, so he familiarized himself with the line very much, so he could talk like blah, blah, blah. So that was really nice. And then talking about the introduction part, here you talk about these complicated issues where you have this complex topography, monsoons, currents, but we don't see any of these here. We see only Taiwan Strait. So that was a little bit funny because, you know, there are a bunch of paper for the topography, for the currents, for the monsoon winds, and you can even add your own cartoons, but you didn't do that. I hope that you can improve this next time. Okay. And another issue for you to improve is, although I know this is probably because here their objective is quite neutral. They only want to know what is influencing the hydrography. But at some point, either in introduction or in, for example, in introduction, you talk about when you can show the direction of currents and wind, then maybe there's one thing you should do. You can introduce how wind can affect upwelling. What is the underlying physics? Because this is not a special case. This area is not special. This kind of phenomenon can be found everywhere on Earth, the wind-driven upwelling. So please introduce the physics behind. And after you say that, it will be clearer to them what is really going on. Yeah, I think since you have only this, I would say why don't you use larger fonts as large as possible? No? Okay. In fact, while they say they are working on Taiwan Strait, in my opinion, they only work on Taiwan Bank. And you should say, this is Taiwan Bank. Yeah. Print it. You just say it. You just said it. But you should print it. Okay, on the map. Where are you referring to? Taiwan Bank. I don't really know if this is necessary, considering you use almost 12 minutes. I think this is probably not necessary. Okay. And this kind of information is more useful. Like you say, how this kind of transect is converted to this kind of 3D map. So this is useful. The introduction of this is nice. Like you take time to introduce each of these different water masses. This is useful. So this part is good. What is this? I don't think this is necessary. Okay, because here you want to show, or you have to do it shortly, maybe because at the end your discussion circle around this kind of data, right? Your discussion circle around this. So when you introduce this, maybe you can say this is the original data, and this will be converted to this, and you only show one case. That's enough. That will be enough. You don't need to show all this. Okay. And then you can have time to discuss more on this. And the way you discuss this is like you describe the feature first, and then this is the factor, the wind factor that the author thinks should be influencing the currents, right? But the way you show this is not very helpful for us to understand this. Okay, so you can show it shortly to say the author thinks the wind is play a key role because you introduce the effect of wind at the beginning. So you can say, okay, it's very reasonable for the author to think the wind is playing a role. I hope that next time you can like put this next to this. You have space here, right? It will be much clearer for us, okay, to see, okay, what kind of wind is affecting the upwelling. And then this is fine. Keep it short because numerical simulation doesn't add new things, okay. And actually, you can even take this out because I feel that you didn't say it very clearly. No, I don't think you say it clearly, like a topography, like a, you just want to say there's a deep channel here. And
this paper they didn't show even any topography here. So
yeah,
I just mentioned it myself.
I know, but I don't know what does this one really tell us, you know? Like you say it affect water mass. How? To me, it probably just affect the way water is moving, not water mass. So you probably need to tell us how does this really affect the water mass you are talking about. Like usually when we say topography affect water mass, that usually refers to topography-induced upwelling, for example. Do you have that here? Something like that. So you have to think of what do you really want to say with topography. Because you are talking about water mass. Okay, if you don't think you can figure it out, then you can take more time explaining here. But you have 12 minutes, so you don't really don't need to say that much. Okay, and this is nice. This kind of concluding remark is nice. But I think to say this, you should provide a better background preparation for the audience. That means the physics of wind-driven upwelling. Provide that next time. Okay, good. So thank you, Bruce.